partons produced from initial hard scatterings, and they are back to back, and they have a high virtuality. And once these high energy partons are produced, since they have a high virtuality, they will do following up further radiations. Like they will do collinear radiations, they will also do soft radiations. So we have a shower of particles produced from the kind of radiation of the initial high energy parton. And these showers just like evolve in time, and eventually they become particles which can be detected in our detectors. And then once we collect all the particles produced from the high energy collisions, we will apply a jet funding algorithm. And depending on the algorithm you use, we can define many jets with different sizes. I mean, by size, I mean the cone size of the jet, which is radius r here. And here is another example at LHC measured by the CMS collaboration. Basically, in the hard collisions, we have kind of two back-to-back jets produced, like they're labeled by these dark regions here. You see a lot of tracks accumulated in this kind of collinear region. And then the CMS can apply a jet funding algorithm to reconstruct some jets. And here we find almost 600 GeV jets here. And in the phi and eta plane, eta here is a rapidity, like describing the beam direction or longitudinal direction. And the phi is the transverse angle, like in the plane that is perpendicular to the beam directions. And if we look at the energy distributions in the phi eta plane, and you see two kind of peak locations here, and they're indicating basically two back-to-back jets. And we also measure jets in heavy ion collisions to study the property of the quark-gluon plasma. Here I show you a cartoon, like when the jet is produced and doing the shower to produce small particles, these particles can go through the quark-gluon plasma, and when they go through the quark-gluon plasma due to the interaction with the soft medium, they may lose energy due to the interactions. And eventually we will find some final jets that have fewer energies than what we have in the beginning. And it turns out that a jet that has kind of wider distributions will lose more energy than a narrow jet. And that is just a reflection of color coherence. Like when the particles are narrow, like they kind of scatter with the QGP more coherently. And as a result, they have a kind of a smaller color charge, and that is why they lose fewer energy. While a fat jet has wider distributions, the QGP can resolve each individual particle inside this jet and interact with them individually. So each particle inside the jet will lose energy almost independently for this wider jet, and that is why a wider jet loses more energy. And it turns out the gluon-initiated jet, which is produced by an initial high energy gluon, it tends to lose more energy than a quark jet, because a gluon-initiated jet, it radiates more, have wider distribution. That's why it's fatter, and that is why it loses more energy.
Xiaojun, can I ask one quick question? So yeah, already, sure. I mean, there is a color factor for the gluon. Well, if the initial part one is a gluon, so it can interact with the medium a little bit more because of this extra color factor, and that already will give you more energy loss in the gluon jets, right? So are you saying this is an effect on top of that?
Yes, right.
Okay.
Yeah, gluon has kind of more color in some sense and interacts more with the QGP. But on top of that, the gluon jet also radiates more widely. Like if you look at the distribution of the particles inside, the gluon-initiated jet tends to be fatter or wider in the theta distribution. I mean, theta is the angle with respect to the jet uses, but quark is narrower in that sense.
Okay, thanks.
Yeah, sure. Yeah.
Sorry, Xiaojun, when you say gluon-initiated, there is also the particle count inside a gluon jet, right? Which is typically larger than the particle. If I collect, for example, the number of hadrons inside a gluon-initiated jets, right? Mm-hmm. That number itself is larger, so it some way tells you also that you are losing more No, I mean, if,
yes, right.
but you are talking about angle, not about particle. So that's what I'm a little curious.
Okay, sure. Yeah. Like you're definitely right. The gluon jet contains more particles, but if all of these particles are collinear or collimated along a single direction, like if they're completely coherent, then they don't behave like multi-particles, right? Like to the QGP, they just behave like a single particle from the perspective of color coherence. But since they have a kind of a wider distributions, right? They're like, if I have two partons, they have a relative large angle in momentum space, then the QGP can resolve each of individual particles and interact with them. Otherwise, if they are collinear, they are like just like due to coherence or due to quantum interference, in fact, they just kind of interact as a single particle to the QGP.
I see. So is this related to glue to QQ bar splitting? Because that in general gives you a wider angle, but fewer times, but still gives you wider angle rather than large number of collimated glue to glue emissions.
I mean, you include both glue to glue or glue to QQ bar radiations in the picture.
I mean, glue to glue is still enhanced, no? I mean, collinear enhanced. Right. So, but the wide angle thing you're talking about, that probably only going to come from glue to QQ bar, no? Or am I missing something?
Yeah, but here it's mainly like the medium induced. Since the gluon has a kind of larger color charge, it accumulates virtuality more quickly than a quark jet by interacting with the QGP. So that's why in the QGP, the gluon jet likes to read it more. Yeah.
Okay.
Sure. Yeah. Thanks for the question. Yeah. So then it's a motivation, right? Since the gluon jet and the quark jet sort of have a different energy loss rate inside the QGP, we're asking the question that if we can separate the quark-initiated jet from the gluon-initiated jet in the final state or in the final data sample, we may be able to use that to better constrain properties of the QGP, because we can study intensively quark jet or intensively gluon jet. That's the goal. And but it's hard in practice, because the jet observables or jet data samples we collect in the end contain both quark and gluon contributions. For example, for observable X, we have both quark contributions XQ and the gluon contributions XG. And they have different fractions FQ and FG here. From the experimental measurements, we only know the final distribution of the total observables, the X. But here, our objective is to know the individual distributions of XQ and XG, and also learn the fractions of FQ and FG. And that is kind of depicted in this picture. So the solid line is the total observable X, and it contains both a quark contribution depicted by this blue dashed line and the red, and the gluon contribution from the red dashed line here. And we want to do a quark and a gluon jet disentangling. Like we want to extract the individual distributions of the blue curve and the red curve. And I motivated this project from the heavy ion perspective. There are also other reasons that we want to do this quark and gluon jet discrimination. For example, if we can do that, then we can understand the QCD jets better. We can study a gluon jet, we can study quark jet, and they have different vacuum showers. And as I said, we can use this to improve jets as a probe in quark-gluon placement. We can also use kind of the individual studies of quark and gluon jets to better constrain parton shower generators such as PACEA. And finally, like people propose a lot of beyond standard model physics, and these physics are either more sensitive to quark jet or more sensitive to gluon jet. If we can separate quark from gluon jets, we can increase the sensitivity in our searches of beyond standard model physics. Okay, so the question we try to address is whether we can extract quark and the gluon jets individually and obtain their fractions from a final total observable. And there has been a lot of studies along this direction. a popular approach is to use or to rely on the Sudakov factors using some jet substructure observables. Like if we look at these jet substructure observables in the tail region, the distributions typically look like this. So the quark contribution has a Sudakov double log. Similarly, that's the gluon distribution, but the coefficients of the Sudakov double logs are different. Like for a quark distribution, the double log coefficient is proportional to CF, where CF is the Casimir for the fundamental representation. While the gluon distribution has a coefficient CA, which is a Casimir for the joint representation, and these two numbers are different, and that leads to a difference of these two distributions in the tail region. Like if you look at the tail regions here, the kind of gluon distribution is more suppressed, is actually more suppressed exponentially than the quark distribution. So if we measure the observables in this tail region, we can see out of say 90% of confidence, the sample is purely gluon. But this approach has two kind of disadvantages. The first one is in this tail region, the experimental data may have a significant uncertainty, and that leads to a large uncertainty in the extraction of quark jet and the gluon jet. So that is why it is not 100% efficiency. And also in this tail region, the kind of gluon distribution never goes to zero. So you will never reach 100% efficiency either. And that motivates us to kind of think about the different way to construct pure quark or pure gluon observables. And here is what we can do in this talk. So I will give a preview of the final results, then I will explain how we construct these observables. So here the Q is a pure quark observable, and this G here is a pure gluon observable. And we construct that using some jet mass observables. So the x-axis here is just the jet mass in the log scale divided by the PT. And in this plot, you see that the gluon contribution to this pure quark observable starts to become vanishing at -4, and it becomes constantly vanishing throughout, like from -4 all the way to 0, or to negative infinity, while the kind of quark contribution is non-zero in the corresponding kinematic region, and there is a large gap between the quark contribution and the gluon contributions. So if we carry out a measurement in this region, we can 100% sure the data we get is a pure quark contribution. And similarly for this pure gluon observables, like the quark contribution devoted by this kind of blue band is constantly vanishing after -4, while at the same time, the gluon contribution is largely gapped from the quark contributions. And again, by using these observables, we can collect pure gluon samples. So this is kind of the preview of the final results that I'm going to show you. And to understand that, we need to I need to introduce some backgrounds to you and explain how we construct that. So here is the agenda of my talk. The construction is based on collinear job grooming technique. So I will explain the collinear job. And to do that, I will explain jet mass in a typical jet measurements without any grooming. And then I will introduce the grooming called the soft job and explain the jet mass measurement in soft job. And then I will use soft job jet mass to construct collinear job jet mass. And I will explain that. And then I will show you some relevant modes that contribute into the jet mass in the collinear job, and show you some factorization formulas to describe the jet mass in collinear job. And once we kind of understand how jet mass works in collinear job, we can use the jet mass to construct some observables, and we will consider the jet mass in both perturbative and non-perturbative regions. And we will use that to construct the pure quark and pure gluon observables. And then I will show you results with the precision at next leading log, and then compare that with some Monte Carlo studies. And in the end, I will draw my conclusion. Okay, so the first part of my talk will be discussing jet mass and the jet grooming. So let me start with the case without any grooming. So we want to measure the jet mass in the end after we reconstruct some jets. So the jet mass is basically defined by the forward momentum of the jet square that. So by forward momentum of the jet, I mean we take each kind of each component of the jet, and we sum over their forward momentum, and that is the total forward momentum of the jet. And we square that, we get the jet mass. And in the high energy limit, by that I mean the kind of jet energy is much bigger than the mass that we measured in the end. And in this limit, we can write this jet mass in this way. So the P minus is the kind of big scale here, or the large scale here. It's the hard scale Q. And this times the sum of all the small plus component of the kind of content of the jet. And to understand the jet mass measurement, we will look at a plot where the y-axis is log 1 over z and the x-axis is log 1 over theta. And the z and the theta basically are used to parameterize a typical momentum inside the jet. So for typical kind of particle inside the jet, we specify its forward momentum using this way. So there's a kind of longitudinal momentum fraction, z, and then there's angles in the transverse plane. So these three components are the minus components, the plus component, and the perp component. And since for a narrow jet, the theta is small, so the plus component here is very small compared to the minus component, and the perp component kind of sits between. And the jet mass parametrically scales like the large scale squared, Q squared, times Z times theta squared. So we can then represent this formula here in this plot. And this jet mass is represented by this blue solid line here. So you just take log of this equation and you find this line here. And this line intercepts with the x-axis and the y-axis at the two positions. And at this position, when the jet mass measurement meets the x-axis, we call this collinear mode. Because for a small r jet, this theta here is small, and that is why we call it collinear. And here it also has a large z, so it's energetic. And the mode sitting here scales in this way for the forward momentum. Like the angle is basically given by the jet mass divided by Q. On the other side of the line, we have another intercept. And this one has a typically very small z here, and it is also large angle. Like remember, this is 1 over theta. So here, the smaller x-axis means larger angle. So this is a wide angle soft radiation here, and we call this soft mode. And the soft mode scales kind of uniformly in the angular distribution. So the theta is on the order of 1, and the z is basically given by mg. Mg squared divided by Q squared. So this is a soft mode here. And using this formula here, we can see that the contribution to the jet mass comes from the collinear mode and the soft mode, but only the plus component of their momentum matters, because the P minus, when you sum over that, it just gives you the original high energy scale Q. And this relation here, this kind of linear relation in the plus component, leads to a convolution when we try to write down a factorization formula describing the jet mass distribution. So this is the jet mass cross-section. The cross-section can be written as a hard function times a convolution between the jet function and the soft function. So the jet function here describes the dynamics of the collinear mode, and the soft function here describes the soft mode. And since the soft mode and the collinear mode contribute in this way to the jet mass, there is a convolution here. So the convolution will connect these two modes at these two ends. This is the kind of factorization description for jet mass without any jet grooming. And now I'm going to introduce one popular jet grooming called soft drop. And let me define soft drop first. So soft drop is defined in terms of two parameters here. One is called z-cut, the other is called beta, and it is described by the following procedure. So we start with a jet that is reconstructed by using anti-KT algorithm with a given radius r. And taking all the kind of components of the jet, we recluster the jet using the Cambridge-Asian algorithm, which is just another jet finding algorithm. But this one has some nice features that I will explain in a minute. And in this algorithm, we first combine pairs with the smallest sort of angular distance. We call it delta Rij. It's basically we pick up a parton I, we pick up another parton J or particle J inside the jet, and we calculate this quantity. And in the small angle limit, this quantity goes like the relative angle between the two particles and the rapidity of the jet. So it's kind of linear in the relative angle between these two particles. And when this object delta R is small, it means the angle between the two pairs is small. So by kind of doing this reclustering, we obtain a tree of radiations, and then we just inverse that tree, and then it will become consistent with leading log branching history, which means large angle radiations will happen first. And in the end, it's just like a small angle radiations. And that is closely related to this reconstruction algorithm. And for example, this is a typical tree in the jet radiation history. So we have a one parton or one particle in the beginning, and then they do a large angle splitting here. We have two branches followed up, and then they can do further radiations. And then we can just have a history of branchings here. But the angular between the two daughter particles becomes smaller and smaller as time goes on, or in the later part of the branching. And then we just go through this branching history from the beginning to the end. So we go through every dots of the branching here, and we keep removing the softer branch until a criteria is satisfied. And this criteria is called the soft drop stopping or termination criteria. So basically, we take the transverse momentum of the two daughter branches, the I and the J branches, and we calculate this quantity. And if this quantity is bigger than z cut times this quantity to the beta power, we terminate the soft drop grooming. And you can redefine quantities and write it in this way. So it depends on the theta to the beta square and times a kind of scaled z cut parameter here. If this condition is not satisfied, we just remove the softer branch and go to the next branching point. So here is an example of how soft drop works. So we go to the first branching point, and let us check this condition. Let's assume this condition is not satisfied at this branching point. And let's assume the lower part is softer. So we remove the softer branch completely, like everything followed from that branch. We remove that. And then we move to the next branching point, which is a dot here. And we check this condition again. And let's assume this condition is satisfied at the second branching point. So we stopped our grooming procedure and we keep everything after that. So the kind of solid part here will be the groomed jet after the soft drop grooming. And then we can use the remaining part of the jet to define any jet observables that we want to measure. And in this talk, we will focus on the jet mass after the soft drop grooming. And again, we can define the jet mass as the momentum squared. And again, in the high energy limit, we can write that as a minus component times the sum of the plus component. And we can look at this diagram again, and the blue solid curve is our measurement of the jet mass as we described it before. But now we have a few more lines describing the soft drop grooming. So the soft drop is basically given by this condition. We require the z to be bigger than the z cut times the theta to the beta.
Xiaojun?
Yeah.
Sorry, a question on the last slide.
Yeah.
In soft drop procedure, I mean, instead of CA, just using KT, how do physics change? For reclustering, I mean the KT tree as opposed to a CA tree?
The KT algorithm has a particular momentum weight in the kind of the angular distance, right? So it favors soft stuff to recombine first. Yeah, in that picture you will have sort of large angle and hard splitting in the beginning, and the soft and wide angle radiation in the end. I think it probably will work similarly to the Cambridge-Asian algorithm, but I haven't seen any construction using KT algorithm to do the soft job. Yeah, so to me it seems okay to use KT, but I don't know if there is any subtle issue in the KT for the soft job. I think the motivation that they want to use Cambridge-Asian is because it's consistent with leading log branching history. Yeah.
Right. But you probably have to think of the beta parameter once again, right?
Yeah. Right.
Yeah.
Yes.
Okay.
Right. Here, like if we use a CA, then it just say that to the beta. But if we use KT, then this probably will become more complicated. Yeah. I think once the PT of the daughter parton enters this formula, probably this formula is more complicated, and I mean mathematically the formula will become more involved, or maybe you cannot factorize. Yeah, that's a guess.
Yeah. Okay. Thanks.
You will see how this enters the formulas later. Yeah. Okay, so let me come back to that. This is a soft job termination criteria, and it's represented by this orange dashed line here. And when this orange line meets the kind of measurement of the jet mass, the kind of soft job is terminated. And that's why this orange line is going up here, because we just get rid of all the stuff after that. And this region, this shaded region here, will be groomed away by the soft job criteria. And the remaining contribution to the jet mass comes from the part here. Okay? This part is groomed away. So we only have this part contributing to the jet mass. And now, if we look at this picture, we still have our collinear mode sitting here contributing to the jet mass. But in addition to that, we have two more modes contributing. And one mode is at the intercept of the soft job criteria and the jet mass measurement. This one is sensitive to the jet mass measurement, and it's kind of semi-collinear and semi-soft. So we call it the collinear soft mode here. And this mode sitting here at the intercept on the y-axis, this one does not know anything about the jet mass measurement because it's far away from the jet mass measurement. So this one is independent of the jet mass measurement, but it still contributes, and it contributes as an overall normalization factor. And we call this scale the global soft scale. So by using the equation defining the kind of orange line here and also the jet mass measurement line, we can work out the scales for both the collinear soft mode and the global soft mode. So for the global soft mode, we can work out its angular parametrization, its kind of Z parametrization, and also its scale. And similarly for the collinear soft mode. And in the factorizations, we will have a convolution between the collinear soft mode and the collinear mode because both of them are sitting on the measurement of the jet mass. So that is reflected here. So the J is a jet function for the collinear mode. SC is the collinear soft function for the collinear soft mode.
Yeah, just one clarification. So in terms of the mode picture, mode diagram, the collinear soft mode sits on the same hyperbola as the collinear mode?
No, they have different Q or different scale in the end.
Okay, so collinear soft, and the global soft all sit on the different hyperbolas. That's
they're
the
on different hyperbolas.
So it's a pure sket one kind of picture.
Yes, this is sket one picture.
Okay.
Yes.
Okay.
Right.
Thanks.
Right. Yes. Yeah. For the jet mass measurement, it's sket one. If you start to measure some transverse momentum imbalance, then the sket two will become relevant, but not here. Yeah.
Thank you.
Sure. Yeah. And in the factorizations, we have the kind of global soft scale controlling the kind of overall normalization. And again, we have a hard function controlling the kind of initial production of the high energy parton. Okay, and this is a soft job and the jet mass in soft job. And now I'm going to show you how to construct collinear job using soft job. So collinear job is defined by using two soft jobs, where one of the soft job is more aggressive than the other soft job. And that can be represented in these pictures here. So now we have two soft jobs. There's a soft job 1, there's a soft job 2, and a soft job 2 is more aggressive than soft job 1. So this purple line is kind of more aggressive than orange line, so it cuts out more space. And then we just use the kind of a region of the jet that is between the soft job 1 and the soft job 2. And in this plot, it corresponds to this white region here. And all the other parts are groomed away. And for the jet mass in collinear job, we just take the difference between two soft job jet masses. So the soft job jet mass 1 is bigger than the soft job jet mass 2. And their difference corresponds to the contribution from this white region here. Like it's kind of shell between the two soft jobs. And the factorization in this case has been constructed by Ian and Yanting in this paper. And if we look at the formula, we have two global soft functions, and they are sitting here. We have two intercepts, and there are two different global soft functions. And we have two collinear soft functions. And since they're on the same measurement line, we have a convolution here. And we have two collinear soft modes here. And the regional jet function, which used to sit here, is groomed away in the collinear job procedure. And for the factorization, we also have a hard function sitting here. And let's look at some detailed factorization formulas. So the formula can be written in this way. This part knows the jet mass measurement, and this part does not know the jet mass measurement. So this part contains the hard function and the global soft functions. And the hard function depends on the jet kinematics and the jet radius, while the global soft functions knows the kind of collinear job parameters, which are the beta 1s and the z's, defining the grooming procedure. And we can also, and the hard function includes, for example, the parton distribution function that we use to calculate.
Sorry, Xiaojun, just clarification, just to make sure I'm not misunderstanding. So in a very simplistic view, when I take big jet, groom away, let's say the peripheral, and keep a hard core after, let's say, after subdrop or any other pruning. So here you are. The collinear drop jet is simply the annulus, right?
Yeah.
Between two different hard cores, you must just take the annulus of the outer hard jet.
Yes, right.
It's a weird object. Okay.
Yeah, it's weird. Yeah, if you think of a jet as a cone, right? Soft job removes the kind of edge stuff, but in collinear job, we also remove the hard core stuff, and then you look at shell region or annulus. Yes, right. Yeah. Thank you for the question. I hope it gives an intuitive picture for collinear job. And now we'll come back to look at some formulas again. So yeah, I just described this normalization, which contains hard function and the global soft functions. And then we look at this mass dependent part. And this mass dependent part controls the distribution of the jet mass measurement, and depends on the z count, the betas, and also the measurement. And it is a convolution, so it can be written as a convolution of two collinear soft functions. This is the collinear soft function for soft job 1. This is the collinear soft function for soft job 2. And they are convoluted by this constraint where they contribute to the jet mass in this way. Like this is just a simple formula I showed you in the beginning. Like you take the sum of the plus component, you times the big scale, and you get the jet mass. And people have calculated the kind of renormalization groups and anomalous dimensions for these functions. For example, for global soft functions, at one loop, it has been calculated. You have some kinematics for one gluon radiation, and you also apply the kind of soft job criteria and also the jet fanning algorithms. So the jet fanning algorithm requires that the kind of radiation, if they contribute in the end, they need to sit inside the jet. And for the kind of soft job criteria, the global soft functions kind of fill the soft job criteria. So we have some theta functions here. This is basically just representing the soft job criteria and write that in a nice way, depending on the momentum of the radiated gluon. And then people have calculated this, and people write down the kind of renormalization group equation for these global soft functions in the MS bar, and we can get some RG equations, and they're just written here. Like we have the kind of evolution equation with respect to the scale mu, and depends on some cusp anomalous dimensions and some single logs here. This is kind of non-logarithmic contributions, but sorry, non-double log contributions, but they vanish at one loop. And they,
sorry, yeah, I have a small question actually. Like, I'm a bit confused with the integral structure. How is it much different from the kind of integral which emerges in the case of rapidity divergences? Because there also you get integrals like dk plus over k plus. So how is that regulated in this case now?
Here?
Yeah, these integrals.
Yeah, this one has this integrals has both UV and IR divergence, but both of them can be regularized in the standard dim reg. So you don't need rapidity regulator here. All you need is just dim reg.
Yeah, I understand
Yeah.
you do not require in general a rapidity regulator because your modes sit on the different hyperbolas, right?
Yes, right.
But just because of the structure of the integral which is emerging, which is like dk plus by k plus, and if k plus goes to either 0 or infinity or large, it has a logarithmic divergence. How does it get controlled?
Yeah, the logarithmic. I mean, you have a delta function here that can get rid of the k plus or k minus, but for the logarithmic divergence, you just regular that using dim reg.
Okay.
Yeah, this is the dim reg calculation, and this delta function also kind of replace this to be perp, and you have a log when the perp goes to infinity, and that is regulated in the dim reg. Yeah.
Okay.
Yeah, and yeah, this is for the global soft function. We can repeat a similar exercise to calculate the one loop calculation for the collinear soft functions. And now we have again the kind of theta function representing the soft job criteria, and the sign differs here because the stuff, I mean, in the two different soft jobs are different, right? So in this soft job, we keep the original soft job region, but in the second soft job, we cannot remove the soft job region that used to be kept. We take the part that used to be groomed away, and that is reflected in this negative sign here. Yeah. And also, we need to consider whether the radiation contributes to the jet mass or not. Like in this case, we will contribute, but in this case, we will not contribute. And this has been calculated, and you can find a simple RG equation by going into the Laplace space. And the Laplace space is basically defined by a transformation from the jet mass space to some kind of position space Y. And they're connected by this transformation. And we get the renormalized one loop formula. We can obtain the kind of renormalization equation for this collinear soft functions in this position space or in this Laplace space. And again, depends on some cusp anomalous dimension with some logs and also some non-double log terms which vanish at one loop. And then we just put all pieces together and we obtain a factorization formula at next leading log. And here, instead of showing the differential jet mass distributions, I show you the cumulative distributions. So basically, we integrate the differential distributions from 0 to some kind of cutoff mass, delta m c square. And this is the factorization formula for the cumulative distributions. And again, we have some kind of Sudakov double logs that also appear in a soft job jet mass. But here, the Sudakov has both negative signs and positive signs. And that, which turn out, is very useful in our construction of the observables. I will discuss that more in detail. And then we have some remaining of the kind of log terms in the evolution. We have the jet mass here. And these K terms are just like double integration of the Caspar anomalous dimension with some beta functions. And the omega is a Caspar over the beta function and integrate over some scales. So these are just some factorization formulas, and we can apply it and plot some cumulative distributions. And here we already see some interesting features of this jet mass in collinear chop. So for example, here we consider 800 GeV jet with R equals 0.2. And this is a collinear chop jet mass distribution for quark and gluon-initiated jet. And we choose these parameters for the collinear chop parameter. And you see in this case, like as we go to smaller jet mass regions, the distribution, the cumulative distribution becomes flat. Right? It does not go to zero in the end, it becomes flat here. And similarly in this case, but the value of this constant depends on the collinear chop parameters. Like if you choose a different set of parameters, the constant value can be very small, or it can be some finite value here. And this constant feature is very interesting. And first, let us understand what it represents, right? So in the constant behavior all the way to zero just means there is a significant fraction of jet events where the two soft chop jet masses are just equal to each other, which means the collinear chop jet mass is zero. There's just a significant amount of events that have that feature where the jet mass is zero. And that is why this distribution starts at some finite value. And this finite constant just corresponds to that fraction of events. And this constant feature will be employed in our following up construction. So our idea is basically taking two sets of collinear chop parameters and form linear combinations of these two distributions. And since it is a constant in the kind of non-perturbative region, once we form the linear combination correctly, you can cancel one of the contributions and make the other contribution non-vanishing. So for example, in this case, if I take this curve and linear combine with this curve and adjusting the coefficient such that the red curve becomes zero, it will turn out that the blue curve is non-zero. And that is how, and that is our strategy to construct the pure quark or pure gluon observables.
Sorry,
yeah.
Xiao. I could you explain the flatness? I missed that part. So the flatness that, MC order PT square, delta MC order PT square, the fact that you get a flat stuff, that's on the right-hand side, as well as you get the flatness at a smaller value of delta MC square with respect to PT square. Intuitively, I missed that point. Could you explain that?
Oh, sure. Yeah. Remember, this is cumulative distributions, right? The cumulative distribution sums the differential distribution.
Oh,
from zero.
I see. You're not getting any sample as you move further and further to the right. Is that right?
No, you look like you have a delta function.
Yes.
You have a delta function sitting in the differential distribution at the zero, and when we integrate this over, yes, this constant is just the delta function.
Yeah, that's what I meant. Even if you increase more and more delta m square, you're still just not getting effect in the integral.
That's right. That's right.
Yeah.
Yes.
Okay.
Right.
Okay.
Right.
I see.
Right.
And on the right-hand side, you basically have gotten everything, and that's the reason it goes to 1, basically.
Yes. Right.
Okay.
Right.
Okay. That's the cumulative distribution. Okay. That was the point.
Yeah. It's normalized such that it goes to 1.
Right. Okay.
Yeah.
Understood. And the feature that you observe over here that, for if I take beta 1, beta 2 is 0, then whatever value of z cut that you take for all values of z cut, it still remains flat.
Yeah.
I mean, the turnover, it looks like both of them has some sort of scale, no, at which you start seeing the curve started turning over.
Which turnover, this or this?
Yeah, from the flat. So suddenly you start seeing them turning over, no? So this looked like for both the different values of z cut, the scale associated or shouldn't say scale, but dimensionless number. But there is a mc square by pt square for the similar value of mc square pt square, irrespective of what your z-cut is. You start seeing more jets being included. Non-zero contributions coming away from
this turnover will depend on the z-cut.
No, but I thought I can see that there is no dependence here, and that's what I'm surprised.
Oh, okay. It's like I see. You're saying it's all doing that at negative 4.5.
Yeah, more or less. So that's amazing, no?
Yeah, but we can write down formulas for that, and it turns out they will be different. I think it's just a difference between a log 0.02 and a log 0.05. Yeah, and also the betas here are different. That will also contribute. And
okay.
I would say just a coincidence here. If we choose the same beta but change the z-cut, then it will be different.
Okay, I see. Okay, yeah. Thanks.
Sure. Yeah. Yeah, let me see one more thing about the non-perturbative region. Like this, the formulas we applied is constructed by a perturbative kind of factorization approach, and we kind of freeze some scales and apply that to the deep non-perturbative region. This only reflects the perturbative feature of the deep non-perturbative region, but in these regions there will be significant non-perturbative corrections that we haven't taken into account in our formulas. And we need to kind of put them into the picture. And that is the following discussion. We want to describe non-perturbative physics. I think I should speed up a little bit. So we can solve the RGE equation for the collinear soft function. And for the boundary term in the RGE equation, we have kind of the one loop contributions. And we want to pick up a scale to minimize the log in this boundary term. And the natural choice will correspond to this combination of scales here. But you can see the problem now. Like when the jet mass measurement goes to deep non-perturbative region, this combination of scales can be non-perturbative, and which means the kind of RGE equation derived perturbatively is not trustworthy when we go to the deep non-perturbative region. And that is why we need to introduce non-perturbative corrections. And the way we did that is, in the previous slide, is we freeze the RGE equation at a scale called lambda CS1. And but here we want to kind of improve the description of the non-perturbative physics. And one way to do that is to introduce shape functions convoluted with the perturbative collinear soft functions. So this is a kind of net or total collinear soft function is a convolution of the perturbative collinear soft function with some non-perturbative shape functions, which has to be modeled. And a nice feature of this shape function is that it is independent of the z-cut. And since it's a convolution, we can go to Laplace space and we have a simple product of the two functions in Laplace space. And we can then write this term using the perturbative RGE equation from some non-perturbative scale, from some scale that we freeze the perturbative evolution. And in this way, we kind of defined a kind of shape function in the MS bar scheme. So by that, I mean, we combine the original shape function with the perturbative boundary term in the RGE equation. And this introduces a scale dependence in the shape function, and we call that the MS bar shape function. And in the end, the scale at which we freeze the RGE evolution is kind of cancels out. The dependence cancels out in the final calculation. It's canceled between the perturbative evolution, this part, and the shape function, this part. So this perturbative part has a dependence on the lambda CS1. And by choosing different lambda CS1s, we may need to use different parametrizations or different models for the non-perturbative shape functions. And then we can just use these non-perturbative shape functions to rewrite our next leading log factorization formula. So now our next leading log factorization formula contains a perturbative piece and a non-perturbative shape functions here. And the perturbative part is similar as before, and the non-perturbative part contains kind of a distribution or integration involving the two shape functions for the soft job 1 and the soft job 2. And in practice, we will choose these two scales to be the same when we stop the perturbative evolution. And this defines the scale at which we kind of model these shape functions. And this will be canceled out in the end. Okay, this kind of prepared us well for the real construction of the pure quark and the pure gluon observables. And let us just move on to the real construction of these observables. So we will use the cumulative jet mass distributions in collinear job, which I have defined, and we constructed a factorization formula, including both perturbative and non-perturbative contributions in the small jet mass region. And then we form a linear combination of the cumulative distribution using two different sets of collinear job parameters. And we will choose the same values of beta, but we choose different values for the z-cut. Like there's a z-cut for the A set and the z-cut for the B set. And then we just form the linear combination between A set and the B set. So the A set has a different jet mass, has a different z-cut, but all the kinematic variables are the same. And for the B set, yeah, they have a different jet mass and the z-cut, but the PT, eta, and R and the beta are the same. And then there's a linear combination coefficient called the CG and the CQ times the A set cumulative distribution. And our objective is to tune these CG and the CQ parameters such that the wrong contribution to the observable vanishes. By that, I mean, for example, for the pure quark observable, we require the gluon contributions to vanish by adjusting these CG parameters. So this is the definition of CG here. And similarly, for the pure gluon observables, we would require the quark contribution to vanish. And to do that, we kind of adjust these CQ parameters such that this equation is satisfied. And in general, these CG and the CQ parameters will depend on the jet mass measurement. That is not what we want. And we want to make these CG and the CQ parameters to be independent of the jet mass, at least in a wide kinematic region. And it seems to be impossible to do that, but by using some tricks, I will show you that we are able to make this CG and the CQ independent of the jet mass measurement. And then we can predict this, and then we can construct these observables. So let me show you how that works. So it turns out that we can get rid of the jet mass dependence in the linear combination coefficients by kind of rebeaming or rescaling the jet mass in the A set and the B set. So the jet mass here in these formulas, the dependence is going through the non-perturbative shape functions. And this is the argument appearing in the non-perturbative shape functions. And we can require that this combination in the A set is equal to this combination in the B set. And similarly for the second soft job in the definition. And by solving these constraint equations, we find a relation that connecting the jet mass in the A set and the jet mass in the B set. And they're connected by these z-cut parameters. And also we only have 3 independent z-cut parameters, like z-cut 1 and 2 for the A set and the z-cut 1 for the B set. But the z-cut 2 for the B set is constrained in terms of the other 3 z-cut parameters. And if we impose these constraint equations and solve these constraint equations, we can show that the shape functions in the A set and B set becomes the same. Like we have a single non-perturbative shape functions now. And then the observables can be written this way. The non-perturbative shape functions becomes a common factor for the A set and the B set. And the linear combination works in this way. So we only have the linear combination of the perturbative pieces here. And then by imposing these conditions for defining the CG and the CQ, we find a purely perturbative calculation or construction for these linear combination coefficients. Like the CG is defined by the cumulative distribution of the G in the B set divided by that in the A set. And similarly for the quark linear combination coefficient. And these linear combination coefficients can be defined purely perturbatively because we factorize out the non-perturbative contributions here. And these constructions is kind of initiated in the non-perturbative region, but it also works in the perturbative regions. Like this formula is the same in the perturbative region. And now let us look at the perturbative construction of these linear combination coefficients. At next leading log, using the RG equations, we can obtain an expression of this CG. And first, these CG parameters are mu independent. Like if we have a set of collinear draw parameters, we can calculate it accurately. And here I show you two examples of these CG and CQ parameters. So basically we choose beta 1 equals beta 2 equals 0. And we have two different sets of z-cut parameters like 0.1, 0.15, or 0.05 and 0.4. And you see in this plot, for this case, where we have 0.05 and 0.4, the two linear combination coefficients differ significantly in a wide region of the z-cut parameters, of the z-cut b parameters. While for this case, we're depicted by the dashed lines, like these two curves are almost on top of each other, which means if you want to construct these observables using the dashed lines, you will have a fine tuning in the observables, which is not good. Like we want to separate quark from gluons, we want these linear combination coefficients to be different largely. And in practice means we need to choose the z-cut 1 and the z-cut 2 in the A set to be separated largely, like 0.05 and 0.4, to have a largely separated linear combination coefficients. And that, in the end, will be translated into a stronger discrimination power to separate the quark and the gluon jets. Okay, this is just like one constraint when we pick up parameters. There are also other constraints, like we want to optimize our parameter choice to construct these observables. So first, we would require the global soft scales to be perturbative, otherwise the construction it breaks down. And this is translated in this equation here. And we also want the z-cut 1 and the z-cut 2 in the A set to be largely separated, as I explained in the previous slide. This will correspond to largely separated z-cut 1 and the z-cut 2, and also largely separated z-cut 1a and the z-cut 1b. And then in proton-proton collisions, there are soft contaminations from the underlying event or initial state radiation. And we want to get rid of those soft contaminations. We can do that by using either a small jet radius, or we apply a strong kind of soft drop grooming here for R equals 1. And also our factorization formula requires the z-cut parameters to be much smaller than 1. And now you can see like the last three conditions are kind of competing with each other. For example, here, we want the z-cuts to be largely separated, but the z-cut has also to be much smaller than 1. This will kind of limit us to a smaller region of the z-cut parameters. And also, if we use this method to get rid of the underlying events, this and this will push the z-cut in opposite directions. And in the end, if we use the second method here, it will be impossible to pick up some valid z-cut parameters. So in practice, we will use this first method to get rid of the soft contamination, which is using small radius jets. And then the 2 and the 4 conditions can be roughly satisfied. Okay, so we will focus on small jet radius in the following. And now let me show you some results from the construction. So these are the parameters of our choice. We choose a very small jet radius. And this is a kind of observables in the deep non-perturbative region here. So the kind of this band here, this constant band here, is the kind of perturbative contribution to the pure quark observable and the pure gluon observables. As I said, there is a constant behavior in the deep non-perturbative region, perturbative from the perturbative formula, and that is represented by this constant band here. But after we introduce the shape functions, this curve is no longer constant. It actually gradually approaches 0. In the end, it becomes 0. But still, we kind of have a large gap, at least in a wide kinematic region, between the kind of contributions and the vanishing part. Okay, and this is a distribution in the kind of deep non-perturbative region. We can also look at the whole distribution in the full kinematic regions, right? So this is a deep non-perturbative region that I showed you on the previous slide. And we can also apply the same construction to the perturbative region. where the same construction basically works. We can have some pure quark or pure gluon observables, even in this kind of perturbative region. But we only analyzed the deep non-perturbative region and the purely perturbative region. Like between these two regions, there is some transition regions where one of the soft job needs non-perturbative correction, but the other soft job is perturbative. So we didn't study that in this study, and we called that region the transition region. So we didn't plot the curves in the transition region, but in practice, one needs to kind of analyze that region and connect these two regions smoothly. But here we didn't do that. We only focus on the non-perturbative region and the perturbative region here. I mean, the perturbative the analytic construction works fine by looking at these plots. And we want to check how those things work in real Monte Carlos. And that is why we kind of carry out a similar analysis using PACEA. And so that is a Monte Carlo generator. And this is a construction from PACEA here. So using the same set of parameters, you see the PACEA has slightly different features here. Like this gluon contribution does not go to 0 all the way here and become constantly vanishing. Actually, the PACEA result have some kind of kinks here, and then it goes to 0. And similarly for this case here. And this just like showing some problems in PACEA. Like like this kind of, the PACEA is not tuned, it's not very well tuned to describe soft radiation physics. And that is why it is kind of struggles here. First, it will change the determination of the linear combination coefficients. So the linear combination coefficients used in this plot is calculated using perturbative formulas. And PACEA may favor a different linear combination coefficients because PACEA is not very well tuned to describe soft radiation. And also this kind of failure in PACEA may also change the shape of the distributions. And to kind of solve the first issue, we try to change the linear combination coefficients to make the curve vanish. And let us see how well we can do that. So by using a different set of parameters, like fitted from the PACEA results, we can make this observable work. Like you can see these gluon contributions to this pure quark observable becomes vanishing here. And there is a large gap between the quark contribution and the gluon contribution. So the pure quark observable works here after we kind of tuning the linear combination coefficients in PACEA. However, the pure gluon observable does not work here. Like you see, like we tried a lot of parameters, like no matter how we tune the linear combination coefficients, we cannot make this quark contribution vanishing here constantly. And that just means the quark jet kind of distribution in PACEA has a different parametric scaling from the factorization. Like the gluon distribution has the same parametric scaling as in the factorization formula. That's why we can make the gluon contribution vanishing here using our construction. But the quark distribution has a different parametric scaling. That is why we cannot make it work here. And that's just indicates some problems in PACEA, which needs to be further studied in the future. And yeah, like here in this plot, I just want to show you, oh, by the way, in this plot, I turned off the ISR and MPI effects. Like they are just underlying effects that can cause contaminations. So I turned them off here. And now let us check the ISR and MPI effects. So here are the comparison between small jets measurements and large jet measurements, large R jet mass measurements. So here I show you three kinds of curves. So the PACEA results with ISR and MPI effects turn on, a PACEA with those turned off, and VINCEA results with those turned on. So in this case, you see that the kind of black dashed line and the red curve are kind of similar to each other. They're almost the same in this region and also in this region. This just shows that the kind of soft contamination is minimized by using a smaller jet radius. While in the kind of large jet radius case, you see the dashed black line and the red curve differs a lot, differs significantly here and also here. So this just like demonstrate our ability to tame the ISR and MPI effects using smaller jet radius. And now I will show you the results with the ISR and MPI effects turned on. Like here, we show you both the PACEA and the VINCIA results. Now you see these two are kind of similar.
Sorry, can you go back to the last slide?
Sure, yeah.
So the last plot, the bottom and right plot,
yeah.
Isn't it a little bit counterintuitive that the result of soft drop, I mean, even after I impose soft drop, I still have this large effect of ISR and MPI?
Yeah, that's a very good point. Yeah, that is because we choose, let me see, this plus. Yeah, I believe this plus with the Z color parameter is 0.02 here.
So you are not aggressive enough?
Yeah, the Z cut is too small here. That is from here. Yeah, you're absolutely right. Like if we choose a Z cut to be on the order of 0.15, the ISR and MPI effects will be groomed away by the soft drop criteria, by the soft drop grooming. The problem here is if we want the observable constructed to work, we need the Z cut 1 and 2 to be largely separated. And yeah, that is a constraint. Like if you choose a Z cut 1A to be 0.15, this one probably is 0.5 to make it work. But 0.5, it also challenges this criteria, right? So yeah, you have competing factors that are kind of force us to use smaller jet radius rather than use Z cut to get rid of the ISR and MPI. Yeah, right. And this is shown in this plot. This is very small Z color parameters. That's why the soft drop does not groom the ISR and MPI away. Yeah. Okay. I mean, our final goal is to definitely have the ISR and MPI effects turn on because they exist in real data. We have to get rid of them to make this work. And you see, yes, even if we turn on the ISR and MPI effects, we can still make the pure quark observables work. Like the soft contamination does not change the behavior here. We still have a large gap between the quark contribution and the gluon contribution. This is good here. And still, we cannot make the gluon observables work. And the problem is not caused by the soft contamination. The problem is already here before we turn on the soft contamination. And this is a problem in PACEA, which should be further studied. Well, PACEA maybe should be tuned to describe the soft physics better. And here is not a problem, the ISR and MPI. Okay, so I mean, this is promising, and we are really looking forward to use real experimental data and to construct these observables. And with that, I will stop here. Like in this talk, I show you how to construct some pure quark and pure gluon observables using cumulative jet mass distributions in collinear drop. And the key idea is to use different Z-cut parameters, but rescale the jet mass such that it is robust against non-perturbative corrections, like the non-perturbative effect becomes a common factor in the linear combination. And then I show you some Monte Carlo studies of these observables. We use small jet radius to remove the ISR and MPI soft contamination. And it turns out that the pure quark observable works in PACEA, but the gluon observable does not work. It suffers from a different parametric scaling of the quark jet distribution, and which hopefully will be solved in the future. But for heavy ion collisions, it's less clear that these observables will work because the parametric scaling of the jet mass distributions will be contaminated by the medium responses or the medium induced radiations. And this should be also explored in the future. Okay, thank you very much. I'm sorry I'm running over time. Yeah, I can take a few more questions.
Okay, thanks, Xiaojun. Any questions? Okay, so I had one intuitive question without the non-perturbative effects. So when you showed the first plots where you saw that the gluon jet mass distribution, cumulative distribution, saturated at a lower value than quarks. This is simply saying that the gluon jets are wider in a slightly different manner, because the delta function seems to be smaller for gluons in all the cases that we see, at least.
Yes, right.
Okay. Right.
Yeah, I got your question. Let me think.
So, I mean, it's not just a parametric coincidence that the gluon distribution is lower at the left end, right? It's
yeah. I think it's it's different from that. To really see how wide it is, we probably want to look at the differential distribution. That can tell us.
Right. Okay.
Yeah, I think in some sense you're right? Like for small jet mass, that means it's like collinear stuff.
Exactly, right. Yeah, I think that might have to do with it.
Yeah, but this is after the collinear job grooming, which kind of removes the hard core. So yeah, that picture is not direct.
I see. Okay, fine.
Right. Like, if there is no grooming, then this would mean the gluon jet is wider because it has fewer narrow cores. But the narrow core is somehow groomed away in collinear job.
It tells you less radiation in the annulus, right? Part of it.
Yes.
So there is a lot more radiation in gluon, but that probably are more towards the hardcore piece, which you are removing.
Or it could also be in the soft edge.
It could be in the soft edge or
Yeah. Okay.
Yeah, right. Actually, do you? And one more question: do you have any plot where you show the analytic calculation and then compare to the Pythia one? I was just curious how they compare.
Yeah. Good. Yeah. We didn't overlay the curves, but we can try to see them here.
Okay.
So yeah, this plot and these plots are using the same kind of linear combination coefficients. And let's see here, it kind of turns around at a -2, and that's basically what happened here.
Yes.
And then in this plot, the kind of blue curve goes down all the way to -4. But yeah, you see there's some, there's a king here. We kind of see that king, but it jumps too much in the Pythia. That is different from the curves here. And the more manifestly is this blue curve here, right? This blue curve all the way goes to 0 and -4. This blue curve goes down, but yeah, you see the difference is here. I think this part agrees well, and this part is problematic. Yeah. And similarly for this curve.
But for the gluons, it's different even in the perturbative regime. I think that's the issue, right?
This region is kind of semi-perturbative.
Yeah.
Like this is fully perturbative. Yeah. Now you're almost entering the kind of transition region. Yeah. There will be some like power, like here, the non-perturbative correction will be power suppressed, but in this region, it is still kind of power suppressed, but the power may become 0.3 or 0.4, and which are not included in the analysis. Yeah, you can look at this paper. They talk about both deep non-perturbative region and power correction region. We only include the kind of deep non-perturbative corrections, but in this region, there could be some power corrections. Yeah. But again, like Pythia, soft stuff is the problematic.
Yeah, no, but for it's okay. It's in the intermediate regime where it's problematic. Here, it's problematic also in the perturbative, I think.
In the perturbative region.
Yeah.
Right.
Well, I don't have any further questions. So, anything else?
Sorry, Rishi. I thought the part was saying like around -4. You're talking about this part, right? Around -4.
Yeah.
But I thought that's what he was saying. This is the part when one of the Z cut approaches the part where non-perturbative effect comes in.
Yeah.
A little bit.
Yes.
That's right. Exactly. Right. I agree. Yeah.
So it's not
here.
purely perturbative here.
Yeah. No. I meant to say intermediate regime.
Okay.
Yeah.
I mean, here you can still apply the kind of formula, but there could be some power suppressed non-perturbative corrections, which becomes important.
Right. Yeah.
Okay. If there are no further questions, let's thank Xiaojun again, and thanks, and hope to see you.
Thanks a lot, Xiaojun. That's a nice talk. Very nice talk.
Thank you very much. Yeah, thank you for the discussion.